done with the chapter, with chapter 26. Just a few words about spherical aberration and chromatic aberration, which is not, well, it is interesting because everybody has used different scopes and microscopes and other optical instruments. So what we know is that if you have a lens of any optical instrument that is made of, if those surfaces are spherical surfaces, a lens of this shape is easier to manufacture, but it doesn't have a unique focal point. This means that lights that come in close to the principal axis are going to have a focal point maybe somewhere here. Well, light rays that are coming farther away from the principal axis are going to have a focal point somewhere else. Maybe somewhere else at front. And of course, this is undesirable because in our design, we assume that any light ray that comes in parallel to the principal axis goes on the other side exactly to the same point. So as a result of this not unique focal point, if your optical instrument is not corrected for that, you're going to see the image blurred, a little bit blurred. And how do you prevent this from happening? Well, if you have the resources, instead of using spherical shape of the surfaces, you have to use a different shape. Namely, parabolic is the shape that gives you a unique focal point. And if you don't have the resources to do that, you can do something else. You can restrict your optical instrument so that it will work only with light rays that are close to the principal axis, so-called paraxial light rays only. And in this case, you're not going to have this spherical aberration that otherwise is present if you use, well, what is the problem of using only those paraxial ways? The problem is that you're going to have reduced brightness. You're probably going to have a reduced field of view. So there is a trade-off here. So this much about spherical aberration in optical instruments. The other easy to analyze problem with optical instruments comes from the fact that almost all materials, including the glass that is used in optical instruments, almost all materials have different index of refraction for different wavelengths, for different colors. So this means that you're going to have one focal point for red light, and you're going to have a different focal point for violet or blue light. Again, this is undesirable because the result is going to be that when you're using an optical instrument like that, you're going to see the object that you're observing to be in different colors. You're going to see separated rainbow colors for the optical instrument that you're using in different places. So it's undesirable. How do you fight that? Well, you have to select appropriate material to manufacture your lenses. Material that doesn't have a lot of dispersion, right? This different index of refraction for different colors. This is what we call dispersion of light, and this is what you want to avoid when you're selecting the material for the lenses. Alternatively, you can use compound system, maybe different materials next to each other with mutually opposite dispersion pattern. And this also is used in optical instruments. Okay, let's see remarks and questions and issues. Anybody? So I'm surprised that you're asking for homework questions. This is okay. But the first section of this class has probably 2 or 3 times larger number of students, and they never ask for homework problems. So what is going on?
They're scared.
They're scared of what? Okay, so I was thinking that the good students are in this section, and this was the reason. But you're saying that students that are not so brave are in this section. I don't know what is the truth. How would you rate your bravery? Okay, let's look at some question from the homework assignment. Maybe not all 4 of them today, but let me see what we have. Okay, web assign. Oops. Here. Okay. Okay. Let's see. So problem number 7. Let's see what is problem number 7 from homework assignment from chapter 26. So you have a point source of light. Point source means emitting uniformly in all directions. At some depth and emit light rays. On the surface, you see circular area of light, illuminated by light. What is the radius of that circle? So here is what you have. Here is the surface. So number 7. Here is your source. So here you have n equal to 1, and here you have n prime, let's say, equal to the index of refraction of water, I think is needed here. I think it is about 1.3, but you may need more significant digits. So you just have to check the index of refraction of water. So look, clearly a light ray that comes in this way is going to continue. And a light ray that is coming here is going to be refracted like this. Well, of course, you always have reflected light rays, but I'm not going to show the reflected light rays. Just to keep this. So notice that since the index of refraction of air is smaller than index of refraction of water, the refracted light rays are deflected away from the normal. not closer to the normal, but away. And of course, you have certain angle, critical angle, at which there is no refracted light ray anymore. So this is the critical angle from here to here, call it T critical. H. And well, there is a formula for the critical angle. So in other words, this is going to give you the maximum radius. The critical angle is going to give you the maximum radius of the circle. That is going to be visible by a person located here. So what is this maximum radius from here to here? Call this maximum radius R. This depth is given, call it D. From here to here, call this D. And from here, you can figure out the hypotenuse of the triangle. So you have this. Oh, you don't even need to figure out the hypotenuse. You have to use trigonometric functions. So the radius R is clearly going to be equal to D multiplied by tangent of the critical angle theta c, let's say. Right? Looking at this right triangle that is formed, opposite to the angle side is equal to the adjacent side multiplied by tangent, because tangent is a product of opposite divided by adjacent side of a right triangle, right? That's it. So we need to know the critical angle. D is given. What is the critical angle? Well, the formula looks like this. Well, Snell's law. Let's start with Snell's law. Snell's law says n prime times, let's say, sine of this critical angle is equal to n, which is 1, multiplied by sine of 90 degrees, because this is the 90-degree angle of refraction of the light ray that comes out of the water. Sine of 90 degree is 1. Index of refraction of air is 1. Therefore, the critical angle for our case is 1 divided by n prime, where n prime is the index of refraction of water. And that's it. So the angle itself is inverse sine of 1 over n prime. So take this angle, sine of it multiplied by d, and you have the radius of the circle that is going to be brightly illuminated. And nothing beyond that circle, because of the phenomenon of total internal reflection. Okay. So what is the index of refraction of water? 1.33. Do you need more significant digits there? Let's see. Well, you just plug in the numbers and it should work for this case. Okay. So other issues here. Yeah.
So where does the 2.7 play into the equation?
2.7. Oh, this is the depth D.
Yeah. Oh, that's D.
This is the depth of the source. How much and how far below the surface the source of light is. Right? Yeah, it is almost invisible. but this is the letter B right here.
Oh.
Right, it is almost invisible.
And then do we take the R equals D tangent of the critical angle and turn it into the n prime sine of the critical angle? Or are those two
No,
separate equations?
no, so start from here. Start from here. So here,
Oh.
read this way, and after that, finish with this.
Okay.
This is the end. This is what they're asking. Find the radius, and here is the radius. This way. Okay.
Thank you.
Yeah, of course. Yeah. I wanted to show a demonstration with two slits, and I couldn't find the two slits. In reality, they're right here, but you have to have a normal vision in order to see that this is a two slit rather than a single slit. And look what happens actually with two slits or even a single slit, something that is going to surprise you. So if I pass a light ray, a coherent monochromatic light coming in from a single slit, what are you going to see on the wall? Well, you have to see well, a single dot, right? But you want, let's see. This is from a single slit. And of course, you have to detect something similar from a double slit, but it is going to be harder. Yeah, double slit. Again, a single slit with very low width. So you see that even after you pass this monochromatic light, even through a single slit, in reality, it gets split after the slit, and you see multiple bright and dark spots. So this is the phenomenon that we're going to study. It is called diffraction of light, and this is what we're going to study on Friday. So just get ready for it. If you can read the chapter, it will be even better, or at least part of the chapter. So let's go to problem number, let me see which problem from the homework assignment. Didn't we do problem number 8 last time?
I think we just did.
We did
I
10
would, I
last
think
time.
out of all that list, 12 is probably the most difficult, so I'd probably do
12?
is the most difficult one out of all those, I thought.
Well, you know that I leave the difficult problems for students. And the problems that I don't know how to solve, I give them on the midterm and the final. So
If you're gonna answer all of them, I'd say you should draw them, but if you're only gonna answer a few more, I'd probably do 12.
what the rest of the class say. But look, somebody went to the trouble to write those numbers on the board. Let's start with problem number 8. So problem number 8. This problem is useful because it shows you how simple the optics of a camera is, especially the camera in your cell phone is a single objective lens. That's it. And after that, of course, the light after that is probably transferred to appropriate place, probably with fiber optics, but I'm not sure. I have never opened a cell phone to see how the camera works. But a standard camera is just that simple. The difficult part is the photosensitive layer here. So for this camera, it is probably some film, but for a cell phone camera, it is a semiconducting device. CCD device, charged device, semiconducting device, which is beyond the scope of this course. So look, now in this problem 8, they say that you have objective that is a converging lens, and they give the distance between the lens and the photosensitive film. So in order to have a clear image, you better form that image exactly on this photosensitive film. In other words, in this diagram, DI is this distance, and they give it 0.21 meters is the DI. So just looking at the diagram, you find that DI is 0.21 meters, and it is plus, according to the sign convention, it is a positive number because it is to the right of the lens. Real image is formed. And they give you DO to be 4 meters. So from those two numbers, you can find the focal length of your lens. Right? You have, they're not asking for it, but you need to know what lens you're working with. So the inverse of the focal length is going to be equal to the sum of the inverses, DO and DI. So from here, you determine the focal length of the lens. Once you have the focal length of the lens, here now is the same lens used in a projector. You have the focal length. And you want to form the image on the screen. So now you have a different DI prime. They say the distance between the lens and the screen where the image is formed is 6.1 meters for my version of the problem. They're asking, so now you're using this transparency right here, this transparency, this film, you're using it here. So how far, what is the DO? Now this is your object that you're reviewing. It is upside down, placed upside down. So they're asking you what is DO for this situation. Well, you already have the focal length from the first calculation. You say that the inverse of DO prime inverse is equal to 1 over the focal length minus 1 over DI prime, which is given. And that's it. It should work. So, well, from here you can. Okay. Yes.
Sorry, so because the lens and the film are the same as the projector on the camera, that's how we know that the focal length is going to be the same?
Yes, this is what they say, right? They say that you use the same lens. You don't need actually to use the same film. Right? Here you're producing the film, the image on the film. Here you're taking that image and making it an object. But you can look at any object, not exactly the film. do this projector. They're only asking about the distance between that object and the lens. And so again, in geometric optics, you don't have too many formulas. The only trick there is the sign convention. This is the only place where serious mistakes happen. Okay, let's go to problem number 9 now. Problem number 9. Problem number 9. So a student is reading a lecture written on a board. The lenses of her eye have refractive power. So basically, the refractive power of her eye, which has lens and many layers of different materials, is given. And the lens to retinal distance is also given. So keep in mind that when you're looking at different distances, the refracting power of your eye changes in order to focus on the object that you're looking at. So if you're looking at an object that is closed, you have higher refracting power, smaller focal length of your eye than when you're looking at something that is farther away. So they say that you have focused your eye and the refractive power at this moment is this. So you have this. They say that refractive power is, for me, it is 66.4. 66.4 inverse meters. Therefore, the focal length of your eye, the entire system, is 1 divided by 6.4 in meters, of course, is the focal length. But they give the lens to retinal distance in centimeters. So, and they want the answer in meters. So you have to convert this into meters. And that distance, 1.515, is DI. This is the distance between the lens and the image has to be formed on the retina exactly. So they say that the I for the situation is 0.0515 meters. Again, conversion into meters from centimeters. How far is the object? Well, once you have those two numbers, yeah.
Did you mean 0.1515?
Yes, absolutely, yes. Yeah, good point, right? There is no such a number. 0.1515, yeah. Otherwise, it wouldn't work. Thank you. So from here, you say that DO is 1 over DF minus 1 over DI. Keep in mind that DI is a positive number also, right? Because the image is formed to the right of the lens. So from here, you just find DO. This is part A. Now they want you to figure out the magnification together with its algebraic sign. And well, you have all the numbers given. So you say that, well, the magnification, which is the height of the image divided by height of the object, also is negative di divided by do. They say that HO is 5.5 centimeters. Now you have to switch into centimeters because they expect the answer in centimeters. So you have to say that HI is equal to HO negative algebraic sign times DI divided by DO. And actually, you don't need to change the units because here meters cancel out. And if you keep HO in centimeters, you're going to get HR in centimeters. And that's it. So the negative algebraic sign that you are going to get after you do this arithmetic indicates that the image is inverted. So actually, the optical system of the human eye looks exactly like the optical system of this camera. You see object that is upright, the image is formed inverted. So again, we talked about that. We're seeing the world upside down. Our brain is making it to look upright, right? And again, last time somebody mentioned that there were experiments, people wearing glasses that invert everything that you look at, right? And after a few days, the brain figures it out and it starts, you don't see the world upside down anymore. So the brain is the organ that actually is used also in image formation, in making sense of the world. Okay. Any other remarks, questions, issues? And the last problem from this list. Oh, so problem number 12, people change glasses. And this is, so it is not that difficult problem, but you have to do two problems at the same time. And after that, do part B also. So you have two people. Let's first analyze the first person. So Bill. So farsighted means hyperopic eye, means that you don't see objects that are close well, which means that you need additional converging lens in order to form the image on the retina as it should be. So they say that for Bill, the near point is given. So let's start with Bill. Here is his eye. And here is the principal axis. And they say that his near point, instead of at a normal place that is about 25 centimeters, it is at 125. Here is his abnormal near point. Here it is, call it N. And this distance, they say, is 125 for my version. So let's only deal with Bill first. So his glasses correct the vision to normal near point. That is at 25 centimeters from the eyes. And both wear glasses at 2 centimeters from her eyes. So here is the lens of his glasses right here. Going to be a converging lens. This distance is 2 centimeters for the first problem. So correct the vision to normal near point, meaning that if you place an object at 25 centimeters from the eyes, you're going to see it clearly. Well, in other words, here, let's place an object at 25 centimeters. So here is this distance, 25 centimeters. 25. This, in order your eye to see this object, the lens has to create an image of this object at the place, at the closest place where the eye can see it. And that closest place is at the near point. Therefore, the image has to be created right here at point N. So this is point N. The image has to be created here. Here is the image. And now, let's figure out what is the focal length of this lens, the lens of the eyeglasses. So, looking at the diagram, this is your DO. What is DO for my version? Well, this is 25. DO has to be what? 23. And here is DI. The image is created here, so here is DI. Let's clean here a little bit. Here is DI from here to here. How much is DI? 123, because this 125 minus 2, 123 centimeters. However, DI is a negative number because that image is formed at unnatural for lenses place, to the left of the lens, to the same side as the object. This is not natural for transparent materials. So this is negative. And once we know DI and DO, we say that the focal length inverse is 1 over DI plus 1 over DO. Again, keep track of the fact that DI is a negative number. So from here you find the focal length of Bill's glasses. So notice that this simple arithmetic became possible only after you draw the diagram very carefully to see which distance is what and on what side. So don't try to memorize it. Always, when you have a question related with glasses or contact lenses or similar, always draw the diagram to show what is where. You're going to be requested explicitly to do that in the midterm next week. After that, we have to repeat the same procedure for what is the N for N. So let's do it again in a pedestrian way. So now you have again the eye. And again, you have length. Just distances now are going to be different. Your object is still going to be at 25 centimeters from the eye. So this is still going to be 25 centimeters. This is still 2 centimeters right here. But her near point is a different place. Her near point is here. So near point for her is here, so that this distance is, the near point is 69 centimeters. And again, you have placed the object at normal visible place. This means that again the object is again going to be 23 centimeters, and I'm going to say the object prime in order not to confuse the numbers for Anne and for Bill. And again, you have to form the image of the near point right here. Here is the image. And again, the eye from here is going to be 69 minus 2 is 67 with negative sign. And for her eyeglasses, the focal length f prime inverse is going to be 1 over di. So di prime is 67, right? We're priming the ants. Distances, di prime plus do inverse of do prime. Do. From here you find f prime, the focal length of Anne's eyeglasses. Okay. Now Anne wears Bill's glasses. So this is a separate story now for part A. So here we're ready to answer part A. So now Anne wears Bill glasses. So now for part A, you have the focal length of the glasses is calculated here. Focal length f, whatever number it is. Your image. So you're placing the object. Well, you probably again need a diagram now, but well, we don't have space for another diagram. But okay, let's try to do another diagram now. Now this is eye of Anne, this is eye of Bill, and here for part A, here's the principal axis. Here is the eye of Aaron. And here are the lenses of the eyeglasses of Bill. So the focal length of this lens is known. It is what you calculated first. What is the closest object that can be seen clearly? So if you place an object at unknown distance from the eye, object. So this is unknown distance. I'll call it x. This means that relative to the lens, that distance is x minus 2 because this is 2. She is still wearing a distance 2 from the centimeters. So this is your DO. For this situation, DO double prime maybe, or I don't know. DO double prime, not to confuse numbers again. The image has to be created at the place where she can see it, and that place is her near point. So here is the near point of M. In other words, this distance from here to here is 69. And therefore, you create the image right here. And that image is at distance from the lens, at the distance from the lens, the image double prime equal to the near point is 69 minus 2 is 67 centimeters. And since it is on the to the left, this is with negative algebraic sign. Once you have this diagram, you just say that the focal length is known. You're looking for the O double prime. So you say 1 over G O double prime is equal to 1 over F minus 1 over DI double prime. So DI is a negative, DI double prime is negative 67. With negative sign in front, this fraction becomes positive. The focal length is for Bill, so it is whatever is calculated here. And from here you find GO double prime. They're asking for this distance, so whatever you find, x is equal to GO double prime, add 2 centimeters, and this should give you the answer for part A. For part B, you have to do the same thing. But now you need another diagram and where to do this. Here is the fourth diagram now for part B. Here is principal axis. Here is the eye of Bill. Here are the glasses of Anne with known focal length. Again, 2 centimeters distance. And again, you place the object at some unknown position at a distance from the eye that is unknown. It is distance x. And you create an image of that object at the near point of Bill, which happens to be at 125 centimeters from the eye. In other words, this is your D object triple prime, and it is known, well, it is x minus 2, and this is the image triple prime. So the image triple prime has to be at negative 123 centimeters. The focal length is known. This is the focal length of the Anne's glasses. And again, you say the object triple prime is equal to 1 over f prime minus 1 over di triple prime. And you just find your triple prime, add 2 centimeters, and you're done. Yeah.
If a question like this were on the test, would you require like diagrams for all parts? Because I understand why you would do diagrams for the first two parts, but then after that, you're just using numbers that you already.
I'm absolutely not going to give you this particular problem because it takes long time to do it. If you know how to do a simple problem that involves only the first diagram, this is enough. But you're going to be asked, please draw the diagram as part A. So only from the 4 diagrams, the first diagram is going to be sufficient for the question on the test. Yes.
Is it both types of lenses where if the image and the object are on the same side, the image is going to be negative? Or is the image in a convex or concave?
So for any lens, no matter if it is converging or diverging, if the image is formed on the same side as the object, namely on the left of the lens, the distance is negative. Di is negative if image is formed to the left of the lens.
That's reverse for just.
For mirrors, it is the opposite. For mirrors, it is the opposite. No matter if the mirror is concave or convex. Okay.
Are you gonna send those PowerPoints in the email?
I'll send the conceptual questions for chapter 25 and 26 only, because for 24, at least the questions that I had, and I tried to show them in class, were not well stated, and some of the answers were wrong. So I'm not going to send that one, and I'm not going to use it. But I'm going to send a single PDF, or not PDF, but single PDF file with several questions, and you have seen some of those in class. Not that many conceptual questions, but you have other conceptual questions in the homework. Okay.
Thank you.